Good morning, respected teachers, friends, my fellow juniors. Today, I, Shrawan Rai, am here to present on the topic of black holes. These are some of the topics that we will be going through today in this presentation. Introduction. The idea of black hole was first suggested in the late 1790s by John Mitchell of England and Pierre-Simon Laplace of France. They both proposed the idea of the existence of an invisible star by applying Newton's first law. Then later, in 1915, Albert Einstein predicted the existence of black holes with his theory on general relativity. After that, in the year 1967, John Wheeler, an American theoretical physicist, applied the term of black hole to what it means now. What are black holes? A black hole is a great amount of matter packed in a very small area. It is a place in space which has such a big gravitational field that nothing, that is, no elements or atoms or even light can escape. Scientists can't directly absorb black holes as light cannot get out from it. They are invisible to the naked eye. Space telescopes with special tools can help find black holes. The only way to perceive them is by detecting their effects on other matter present nearby. Formation of black holes. Black holes are formed when massive stars die. Inside a star, the nuclear fuel of a star and its own gravity collide. This creates stability, but when it runs off nuclear fuel, gravity compresses the star. Then the outer layer of the star explodes into a supernova and the center collapses inward due to its own gravity. After that, a black hole is created. Parts of a black hole. These are some of the parts of a black hole we'll be discussing today. The first is the event horizon. This is the part of the black hole where nothing can get out. It is usually defined as a big sphere that surrounds the black hole and which absorbs any material including light. Second, the singularity. This is the part of a black hole in which all the mass has been compressed to a very small space. As a result, the singularity has almost infinite density. Third, the accretion disk. This is a disk that is composed by stellar material, which goes around the black hole forming a spiral. That is, it is a structure formed by diffusing material in orbital motion around a massive central body. Fourth, the ergosphere. It is a region located outside a rotating black hole outer event horizon. The photon sphere. The photon sphere is a place in which gravity is so high that photons or light have to travel around the black hole's orbit. The squared radius. It is the event's horizon radius. It is a region where the escape velocity is greater than that of speed of light, and it is given by R is equals to 2gm by c squared, where g is equals to gravitational constant, m is equals to object mass, and c is equals to speed of light. Types of black hole. Miniature black hole. They were created at the beginning of the universe and are small as an atom but have very large mass. It is also known as quantum mechanical black holes or mini black holes. This concept was introduced by Stephen Hawking in the year 1971. Number two, stellar mass black holes. They are created when a very large star dies and creates a supernova. That is, they were formed by the gravitational collapse of a star. These black holes have masses ranging from about 5 to several tens of solar masses, and are about 10 to 24 times massive than the Sun. Number 3 is the supermassive black hole. They are the largest type of black holes with mass on the order of millions to billions of times the mass of Sun. Observational evidence indicates that almost every large galaxy has a supermassive black hole at the galaxy's center. These are some of the references I used when I was making the presentation. Thank you.
Okay, thank you, Shravan. Do the students have any questions?
Yes, sir, one question. In the beginning, you specified about relativity, like how they use the concept of relativity while inventing or focusing about black hole. Then, what's that concept?
I'm not sure, but like the theory of general relativity predicts that a sufficient compact mass can deform time space. Okay, which concludes or can be predicted to be a black hole. Does that answer your question?
Okay, thank you.
Thank you.
Anyone else has questions?
Can you say what is singularity?
Singularity. Okay, wait. Let me pull up the slide. Singularity, is the most compact space. Like all the matter that is present, it is compact in that area. As you can see in this figure, at the bottommost, there is the singularity. Like, let us say it's like a tip of a cone where everything is absorbed into it. Like let us say what can I say? If there is a whirlpool going out there, as you know, everything is sucked inside, right? At the middle. It's the same thing with this. Does that answer your question?
Okay, thank you.
There's a question in chat, which is, can we say that the singularity is the center of the black hole?
So yes, we can say that. So
okay, does anyone else have questions? Any other students? Okay, Sujata ma'am, any questions from your side?
Sir, you can ask.
Okay, Digvijay sir.
Shravan?
Yes, sir.
Do all stars from after the it runs out of energy, do all stars form black holes?
No, sir, not all stars, sir. Like, uh, it has to be like 10 or more than like no smaller stars can't be created into a black hole, sir, after dying, sir. Like it needs a mass, sir, like a certain amount of mass to to create a black hole, sir. I think it's about, sir, 10 to 20 times the mass of the sun, sir.
Our sun?
Yes, sir.
Okay. and yeah, I think one of you asked the question. Okay, so over to you, Vikramjit.
Okay, thanks, sir. Right. So again, Shravan, good presentation, well constructed. One thing I will mention is the font that you have used for the title of the slide, right? Like the paths of a black hole.
Yes, sir.
I don't know what the font is called, but we kind of call these kind of fonts Gothic fonts. People don't really use them in a formal presentation. Now, I don't have a problem with this. Okay, I'm not saying it's a problem or anything, but if you ever have to do a formal presentation, don't use Gothic style fonts. Okay.
Okay, sir. Okay, sir.
It's kind of out of style now. Again, nothing wrong with it. I think it's perfectly fine. But I still need to tell you,
Yes, yes.
what kind of things going on. So, all right. Do you know how long your presentation was?
So I think it was short, sir.
It's 8 minutes. That is very short for a presentation on black holes,
Yes,
which people can talk hours and hours on. This is a very short presentation. And I'm a little surprised you never talked about the fact that the last year's Nobel Prize was completely based on the discovery of black holes.
Oh,
And we never talked about the image of a black hole, the M87 black hole image that was
yes, yes, sir.
discovered in 2000, not discovered, but created in 2019. You're supposed to have talked about all of that, right?
I put it up in the first slide, sir, but like I didn't discuss it, sir. Sorry, sir.
See, your presentation, it's not just on time, but there are certain things that if you're going to cover a topic, you're going to expect that you're going to cover certain things. And the image of a black hole is the first definitive visual proof we have that they exist. Until then, all our proof was indirect. We were proving it using gravitational activity around the black hole. We were sort of looking at like how the output of the black hole and things like that. Nobody had actually looked visually at a black hole until the 2019 picture of the M87 black hole. It is only after that, even though we had known about black holes for roughly 30 years, it's only after that picture that the Nobel Committee was like, yes, black holes exist. Let's give it to the people who are behind the work. All right.
Yes.
So that's why it's so super important. So if you're going to talk about black holes, you have to talk about that picture and probably the corresponding Nobel Prize.
Okay, sir.
Okay. Just go forward to the slide on the quantum black holes. Oh, go back 1 second. Sorry, just go back 1 second. Yeah, it's pronounced accretion disk.
Okay, sir.
Accretion disk. Okay, now go forward. And it's Schwarzschild radius.
Yes, sir. Schwarzschild.
Schwarzschild radius. Okay.
I kind of missed the pronunciation.
Yeah, yeah, I know it's a German name. It's hard to pronounce. So I'm not going to hold that against you. All right, so go forward one more. Yeah, so miniature black holes. Where are they?
So, like, where are they formed, sir?
Yeah, well, they were created in the beginning of the universe. They're part of GOT theories, but have you discovered any of them?
So I think so, sir. It was discovered, so.
No. Okay, this is important because you need to mention this every time we talk about miniature black holes. They are a theoretical idea.
Oh, okay, sir. Okay, sir.
Okay.
Yes, sir.
There
Yes, sir.
was some fear when CERN was doing their experiments for the Higgs boson.
Yes, sir.
Certain GOT theories predicted the creation of black holes, miniature black holes. Okay.
Yes, sir.
So there was some fear that when CERN did its Higgs experiment, miniature black holes might be created, and some people were trying to block the experiment from happening. But it is such a. But here's the thing: miniature black holes is kind of not a fully supported concept. The idea that they created in the early universe is possible, but again, it's very theoretical,
Okay,
right?
sir. Yes, yes.
So you need to kind of do specify that it's a very theoretical idea.
Oh, okay, sir.
All right. Again, so your presentation was okay, but it's kind of missing a lot of pieces. Even when we go to things like the discussion of a black hole, you never really talked about what an event horizon is going to be. What happens if you fall into an event horizon? What happens if someone falls into an event horizon?
Oh, okay, sir.
Okay. No, my question is, what happens if like an astronaut falls into the event horizon?
They cannot get out of the event horizon, sir.
Okay. What about the forces that work on his body as he goes deeper and deeper? See, as an astronaut goes deeper and deeper into the black hole, because the curvature of space-time is so extreme, the head of the astronaut will have a different gravitation, like the head and the feet of the astronaut will feel different gravitational effects. And it will start stretching out the astronaut. This is called spaghettification.
Yes, sir. Yes, yes, sir. Sorry, sir.
Yeah,
Yes.
which is a brutal idea, but it is a idea that people like talking about, right? Because it's such a,
Stephen Hawking.
it's like a horror movie idea
Yes, sir.
in
Yes,
a black hole, right? See, there are very few exciting things in physics for other people. So we like talking about things like spaghettification and things like that.
okay. Yes,
So
sir.
you want to put all of these things in, right? Again, you're just going through like the basic stuff. You're not really, I would have liked you to go a bit more in depth. Right? You don't have to be talking about general relativity and the equations and all, but at least a little bit more in depth, because black holes have a lot of prominence, especially now because of Inception and the Nobel Prizes. Everyone's been paying attention to it, so it would be nice to go a little bit more in depth on this topic.
Okay, sir.
Okay.
Yes, sir.
Yeah, that's it. I just wish you had done a little bit more development and you had put more you had put more material in. Also, your reference slide. I am not very disappointed in your reference slide. That's not how you're supposed to present references. If you had a nice reference slide, please keep that in mind. Okay.
Yes, sir.
However, I will give you credit for crediting all the pictures. That was really nice. Thank you.
Oh, okay, sir.
Sujata ma'am, questions?
Yes, sir. So, Shravan, tell me,
Yes, ma'am.
so what was the difficulty, okay, in imaging the picture of black hole?
Sir, ma'am, I didn't understand your question, ma'am.
What was the difficulty or biggest challenge in imaging a black hole? Like you can't see black hole,
Yes, sir, ma'am.
okay? Then in imaging a black hole, what is the biggest difficulty or challenge?
So, ma'am, I think it's diffraction, ma'am. Like we cannot see it directly, but like when but when we are like picturing a black hole, like imaging a black hole, we kind of see the other matter present nearby it. So the light that diffracts to the other matter, ma'am. I'm not that certain, but when I was reading it, when I was like collecting the materials, I got some through it, but I didn't go in detail.
Okay, but and another thing, like the first picture of black hole, that was not so clear.
Yeah,
It was
yes,
dull. And what is the reason behind it? Like you are the science people, you can at least understand the reason.
ma'am.
So have you studied that?
The difficulty in like black holes, ma'am, it's one is due to the gases present, ma'am.
No, now I am talking about that image. That image was not so clear. It was dull.
So yes, ma'am.
And why?
I don't really have an answer for that, ma'am.
Okay. Okay then. But after this presentation, at least you search the reason for this, okay? Why
Yes,
the imaging so dull? It's not so clear.
That tiny blurred image is one of the most difficult pieces of astronomical sort of astronomical engineering and computer programming ever done. The fact we even got an image like that is quite impressive. You should read up on it. It took them years to make an image like this.
okay, sir.
Okay. For those of you who are wondering why people study computer programming and physics, that image is the reason why. A large part of it was done using computer modeling and image analysis techniques.
Okay, Shrawan has a question.
So Bayu asks, which will be more painful, falling into a supermassive black hole or a miniature black hole?
Supermassive.
I think they'll both be equally painful. See, the thing about the supermassive black hole is you won't notice that you've crossed the event horizon until it's too late,
Yes, yes.
because it's very gentle. So you'll be floating in slowly. With a miniature black hole, well, imagine something the size of a dime just sucking your entire body or something. So. But at the end of the day, when spaghettification happens, it doesn't matter how big it is. You're going to get stretched out.
Yes, sir.
Okay.
Okay.
Right, anybody else has any questions?